Welcome to video for lecture 10, section 2. This video describes how non-interacting first-order processes in series are combined so that we can determine the final process output and any intermediate values we want. We will use liquid level in tanks and flow from tanks to illustrate the process, even though the concept and the procedure is applicable to any series of non-interacting first-order elements. The examples we will work with will have multiple tanks in series. This video will deal with non-interacting tanks. The next video will deal with interacting tanks. The equations we will generate will be able to calculate the flow rates from all of the tanks and the fluid depth in all of the tanks. This is the sketch we will use to illustrate non-interacting tanks in series. The sketch has two tanks, labeled Tank 1 and Tank 2. The inlet flow rate into Tank 1 is described by Q. The outlet flow from Tank 1 is given by Q1, and the liquid level in Tank 1 is given by Z1. Then Q1 is the inlet flow rate into Tank 2. The outlet flow rate from Tank 2 is given by Q2, and the liquid depth in Tank 2 is given by Z2. The fluid flow resistance values for each tank are given by R of the tank number. For today, we will assume that the flow is laminar, so the output flow rate is given by the tank depth Z over the fluid flow resistance R. Note that the subscripts need to match. Tanks are defined as non-interacting if the tanks are independent of each other, which means that flow and liquid level in upstream tanks are not dependent on flow and liquid level in downstream tanks. We will say that the flow from Tank 1 is not affected by the flow and tank depth in Tank 2 when they are drawn this way with a gap between the two tanks. Here is the mass balance equation after assuming that ρ is constant and the tank cross-sectional area A is constant. We can write the transfer for Tank 1 as Q1 over Q equals 1 over tau 1 times S plus 1. When you do the class activities and problem sets, you can write the appropriate transfer function too. You will not need to develop the transfer function for each tank element. Here is the mass balance equation for Tank 2. For this tank, let's write the transfer function that gives us the fluid depth Z2 as a ratio of the inlet flow into Tank 2, which is Q1. The transfer function is Z2 over Q1 equals R2 over tau 2 times S plus 1. Now let's say that we want to find the fluid depth in Tank 2, which is Z2, in relation to the inlet flow into Tank 1, which is Q. We can find that transfer function by simply multiplying the appropriate transfer functions in series. So to find the transfer function Z2 over Q, we multiply the transfer function Q1 over Q times and the transfer function Z2 over Q1. The result is 1 over tau 1 times S plus 1 times R2 over tau 2 times S plus 1. If we want to find the fluid flow rate from Tank 2 in relation to the inlet flow into Tank 1, which is Q, we multiply the appropriate transfer function in series. So to find the transfer function Q2 over Q, we multiply the transfer function Q1 over Q times the transfer function Q2 over Q1. The result is 1 over tau 1 times S plus 1 times 1 over tau 2 times S plus 1. We can generalize the procedure using these transfer functions. So if we are given a series of transfer functions with a subscript in the numerator higher than the subscript in the denominator, we can find the transfer function for any intermediate value by multiplying the upstream tank transfer functions together. Now let's go over an example 11.1 in the course packet. So we have two non-interacting tanks in series. What we will do is to compare the fluid depth in Tank 1 with the fluid depth in Tank 2. When the Tank 1 inlet flow rate Q changes by a positive unit step change. Tau 1 equals 0.5 second and tau 2 equals 1 second. Both laminar fluid flow resistance equal 1 second per square meter. Given the tau values and R values, we can find the tank cross-sectional areas because tau equals A times R. For this problem, A1 equals 0.5 square meters and A2 equals 1 square meter. The transfer function for the fluid depth Z1 is Z1 over Q equals R1 over tau 1 times S plus 1. The input function Q is a unit step change, so Q equals 1 over S. After making the substitution, we get Z1 equals R1 over S times tau 1 times S plus 1. After we take the inverse, we get the time domain expression Z1 equals R1 times 1 minus e to the minus t over tau 1. For this expression, all the subscripts are the same. We need to find the transfer function for Z1 over Q. We can go directly to the appropriate equation on page 11.2 of the course packet for Z over Q, which is 1 over tau 1 S plus 1 times R2 over tau 2 S plus 1. We are given that Q is a positive unit step change, so Q of S equals 1 over S. For this problem, it is useful to write the transfer function in the 1 over tau form so that we can find the inverse directly in the Laplace transform table. Then we do this and we get the Laplace domain expression Zs, shown here, which is R2 times 1 over tau 1 times 1 over tau 2 over S times S plus 1 over tau 1 times S plus 1 over tau 2. We can invert this using equation 22 in the Laplace transform table. The time domain expression for this fluid depth in tank 2 is shown here. Here is a graph showing the fluid depth of the two tanks. The horizontal axis is time in seconds, and the vertical axis is liquid height in meters. The first tank is the dashed line, and it is the first order response. The second tank shows a response with a delay. Given enough time, the tank depth will increase by 1 meter too. For example 11-2, in the course packet, we can find the tank 2 outflow rate Q2 using the same two tanks and the data from in example 11-1. The appropriate Laplace expression is Q2 over Q equals 1 over tau 1s plus 1 times 1 over tau 2s plus 1. After substituting in the Laplace expression for a unit step change, 1 over s for Q, and taking the inverse, we get this time domain expression here. This slide summarizes the types of problems you need to be able to solve given non-interacting first-order elements in series. You will want to be able to find the overall transfer function for any portion of the series of elements and any of the intermediate fluid depth or tank outlet flow rates. This slide summarizes the solution procedure. You need to identify the system elements and determine whether they are interacting, non-interacting, have a constant flow, or are nonlinear. Then you need to find the transfer function for each element. In most cases, you will be able to write the transfer function using the ones we have developed already. Next, you need to find the overall transfer function. You will need to be given either the time domain input function Qt or the Laplace domain input function Qs. You will use the overall transfer function and the input function to find the Laplace domain expression for the desired liquid depth or outlet flow rate. Finally, you need to take the inverse of Laplace domain expression to find the desired time domain expression. This brings us to the end of this video on how to analyze non-interacting first-order process in series. Please write down any questions you might have and bring them into class.